Okay, we're going to talk about converting between the two vector forms, where we said that vectors can be given in component form, say this like this xy, like 3 comma 2 is right 3 and up 2, or they could be given in magnitude and direction, r and theta. The r is called the magnitude of v, which we would represent with these double value, uh, like double absolute value things here. Uh, we use a little arrow over the v to indicate that it's a vector. Some people will just use boldface for vectors, but I find that's kind of problematic because it's especially drawing these by hand. It's really hard to tell a boldface from a regular face. Okay. Um, Everything that you need to know is all related in this triangle right here, right? So here's the vector, blue vector here. In this case, it's the vector 4, 3. And so you can see the components are given by the legs of this right triangle. The direction angle is this theta that it makes with the horizontal here. Not just with the horizontal, but to the right. You know, a vector going from 0 to the right here. What angle does that make? And then the radius, or the magnitude, is the radius here of a circle, if we made this into a circle. So we often use the letter r for that. And that's the distance across here. Well, we've looked at these many times before. For example, x over r is the cosine of that theta. So solving for x, it's r times the cosine of theta. And similarly, y over r, that's opposite over hypotenuse, is the sine of theta. And so in general, we get r sine theta is y. And this works when we think of theta as going around the circle and not necessarily just being an acute angle that you get inside of a right triangle, or even necessarily an obtuse angle. It could be any real number for the theta. So now we're thinking of the theta as being a rotation there, not just a physical angle measurement. So if you got r and theta, that is magnitude and direction, we can get to the x and y components real simply like that. If you want to go the other direction, then of course, if we know the x and y components, we can use the Pythagorean theorem to find r. So r, or the magnitude of v, is the square root of x squared plus y squared. And the cosine of theta is x over r. So remember, r is the square root of x squared plus y squared. So if you have x over the square root of x squared plus y squared, that's cosine of theta. And so if you do theta is arc cosine of this, that will work just fine if your angle is in the first or second quadrants. If it's in the third or fourth quadrant, the way this thing is pointing, then you want the opposite of that. So notice when y is positive, you get the arc cosine of x over square root of x squared plus y squared. And if the y is negative, you get the opposite sign of that. So that is, you're taking the sine of y, SGN of y. That's SGN of y produces, well, 0 if y is 0. And it gives you -1 if y is negative. It gives you +1 if y is positive. That works for every single thing except for one that's pointing directly to the left. Because directly to the left would be, theta would be pi, or at least that's one option for it, and this would return 0 instead. So this formula works everything except for that. So let's say unless what do we say? Unless y equals 0 and x is negative, then theta is pi. Okay, so that is that gives you that. So we some real basic triangle trigonometry there. gives you this setup. And you end up doing the same kind of computations over and over and over and over again. We did it with solving triangles. We do it with vectors here. You do it when you're doing rectangular versus polar coordinates. Uh, these same constructions, same computations come up many, many times. So here's an example. Suppose we're given the vector v is 2, 5. That's component form. Then we can compute its magnitude and direction like this. The magnitude of 2, 5 is 2 squared plus 5 squared and then square root. Well, 2 squared is 4, 5 squared is 25, 4 plus 25 is square root of 29. So the magnitude is exactly square root of 29. Pull out a calculator, that approximates to about 5.38516. The cosine of theta then would be the 5 over this r. No, that's incorrect. 5 over, okay, I've got it right there. It's 2. Okay, yeah. X over r, 2 over square root of 29. So theta is the inverse cosine of 2 over square root of 29. Or with the 5 and 2, 5 over 2 is the tangent of the angle, so it's the inverse tangent of that. Since you're in the first quadrant for this angle, both x and y are positive, you can use inverse tangent or inverse cosine equally well. Just make sure you have the right numbers inside here, and you get either way in radians 1.19029, or in degrees approximately 68 degrees or so. Okay, now what if you go in the other direction? So this was taking component form and going to magnitude and direction. So what if we have magnitude and direction? So let's say we have a vector with magnitude 6 in the direction of, say, 20 degrees. So how do we do it? Well, in component form, we use these little, this is the notation we're using for vectors, x, y. Well, it's just r cosine theta, comma, r sine theta. So that's 6 times cosine of 20 degrees, 6 times sine of 20 degrees. We could convert the 20 degrees to radians we want, or just leave it degrees. And either way, get it in a calculator, and you get, that's about 5.6 to comma about 2.05, roughly. Okay. So here's an exercise for you, exercise 5. Compute the magnitude or direction of the vector 3, 6. Do it, algebraically, numerically, like we've got up here. Now, then the next thing we want to do is actually draw the thing out. So take this and actually, using this grid, graph a vector 3, 6, actually then measure its magnitude, where one of these is 1 unit. So if you've got some paper that's like automatically 1 centimeter apart on the grid, that works nicely, because then you can just use a centimeter ruler to measure it. Okay? Or take your compass, and now that what you have the vector drawn here, rotate that around to where it's either vertical or horizontal, and then count how many squares up you go, and a fraction of a square if it's not perfectly a whole number. Okay, so measure that, and then use your protractor to measure the angle. Whether you're doing that in degrees or radians, you can figure that out. Of course, if your calculator's in degrees, the output of these inverse tangent or inverse cosine functions, they will be in degrees. If your calculator is in radian mode, the output will be in radians. Okay, and then exercise 6 now. So let's do one the other way. We want length 7 and 30 degrees. And then go ahead and find the magnitude and direction there. Use your knowledge of some special triangles to get this value exactly. It might have a radical or something in it, possibly, maybe not. And then go ahead and approximate it to 6 significant digits using a calculator. Okay? So you're going to find the x and y components of that. Now then again, I want you to do this on a piece of paper. This time you could have one without lines. Just make you an axis there that you can measure from. So you have a horizontal and vertical. Pick a point on there. and mark out 30 degrees, measure a length of 7, and then pull your perpendiculars down and measure those sides of that right triangle and make sure that they match what you computed. Okay, so make sure it works there. Okay, so that's a quick introduction to vectors. We've talked about what a vector is. We've talked about how to add and add them at least, and we've talked about how to change the component forms. And then that's all we're going to need to get started with vectors. There's a lot more you can do with it. I refer you to my playlist in my calculus class section of this for more work with vectors. But for now, we're going to go on to seeing how this can work with transformations in the next video.